but I don't think we've seen any other radical reactions. Let's look at radical bromination. Can you do chemistry with a simple alkane? If you look at simple alkane, it really doesn't have any traditional reactivity because it can't act as a nucleophile. It doesn't have a leaving group. So what type of, it doesn't have a pi bond, so it can't do alkene chemistry. So what can it do? Or in one of our first handouts, first test, we just said you can burn it, combustion, and you can cook your hamburgers, right? We showed that. But we also showed in that original handout you can also do radical halogenation. And we would do that later in the course, well, later is now. If you treat an alkane with elemental bromine and either light, this is H nu, Planck's constant in frequency, that's light energy, yeah? Or heat, energy from heat, or peroxide, we can get a reaction. And we can do a bromination. This is a substitution reaction because the H here is being replaced with a bromine. H is leaving. But we don't call it a leaving group because it's not traditional like substitution or elimination. And H would never be a leaving group in those reactions. But this is a substitution reaction. All right? It's a radical reaction. What else is formed in this reaction?
HBr.
Yes, HBr. Okay, that's just the fate of the H and the other bromine. HBr is also formed. Okay, the reaction is usually regioselective. That is, the bromine is going to end up only on the, I won't say only, but primarily, it's going to be selective for which carbon? Tertiary carbon, right? Okay, so here we're doing a radical bromination of the tertiary carbon. It's going to be selected for that carbon. Why? We'll see in the mechanism. We can compare this to if we had an alkene reacted with bromine. We know alkenes react with bromine to do what? Addition. Bromine adds across the pi bond, you get a bromine on each carbon, and that's it. There's no other product. The bromine is adding to the alkene. Okay? But up here, we're replacing something, and the something that gets replaced ends up over here. It's a substitution reaction. Only one bromine in the product up here, and down here we got two bromines. Addition reaction. And down here, this is pretty darn easy, quick, no extra energy needed. You've done this in lab, it's almost like a titration. As soon as you drop in the bromine, the pi bond reacts pretty darn quickly. Okay? Because the pi electrons are not as tightly held, they're more free to act as a nucleophile and go attack the bromine, which can become polarized, it's schizophrenic. Okay, it's easily polarizable. All right, so what's the mechanism for a radical bromination? And why do we get regioselectivity? All right, the first step here is the bromine bond gets ruptured. Broken here. Your halogen bonds are fairly weak. You can look at bond strengths, but they're fairly weak. I would say because these halogens, they don't like to bond to each other. They're kind of, all right, it's a weak bond. And with a little heat or light, okay, maybe a light bulb or something, we can shine some light. It's like light being shined in here, light energy, all right. And this will lead to the bond being broken. One electron will go onto this bromine, and one electron will go here. I can't draw a light bulb, but it's kind of light or something, light bulb. I'm the worst artist in the world. And we're moving one electron, and when we move an electron, we do a half hook arrow, a fish hook arrow, yeah? One that way, this way. What does that give? Well, there's 3 lone pairs here originally, and this moves here, becomes what? Just one lone, not one lone pair, one electron. Right? One electron moves here, 3 lone pairs, 1 electron, 3 lone pairs, 1 electron. Instead of redrawing that again, can I just say 2? Is that okay? This arrow movement gives 2 of those. What do you call something with a single unpaired electron? Yeah, this is a radical bromine. What's the charge of the bromine? Charge of that bromine. How many electrons does it own? 7. How many is it supposed to own? 7.
Oh, yes, yes.
And so what's the charge? Neutral. Of course, a neutral molecule is going to, whatever it does, everything's going to be neutral. You can't just create charge. Okay? It's 2 neutral bromine atoms. They do not have an octet. It does not have an octet. You might think that these 2 would like to team back up and make a bond. Possibly. But with energy, it breaks. And this is driven by entropy. 2 atoms break, 1 molecule break it into 2 atoms. Just like if I drop the glass here, it would shatter. Okay? All right? Could this come back? Is this an equilibrium? It probably is an equilibrium. I mean, these could join back up and remake bromine. Okay? Yeah, it's probably an equilibrium. We get bromine radicals. Well, this can do something else. It can go on. The bromine radical, all right, will, what I call is strip the H out. This electron will go and team up with one of these electrons. And one moves here. And the other electron in this two electron covalent bond moves on to carbon. Now, how does this actually strip this out? You know, this electron probably gets close to these 2, but this H will just kind of, instead of having its electron teamed up with the carbon electron, the H electron will team up with this electron. And we're showing that very simplistic here, and you could probably have a book this thick on this magic of this bonding that's taking place. But what does this arrow movement give? Well, what's on the carbon now? The H is gone, but what did we leave behind there on that carbon with that arrow? 1 electron. Yes. This 1 electron is teaming up with 1 electron from H. So what did we make here? Plus HBr, right? And now that is 1 electron from bromine and 1 electron from H to make the covalent bond. That's what we did here. What did we produce? We made a tertiary radical on carbon. There's our HBr, which we said we were going to form. Okay? How do we get this product? We could team this carbon electron up with a bromine electron and make a 2 electron shared covalent bond. Now we get that, right? Okay. Do we have another bromine radical?
Yes.
Yeah, we actually had 2 here. But that's not the mechanism. Because if we use the other bromine radical here, that means we just made 1 product. How would we then make the second product? Because when you do this, you can make a gram. You can make a gazillion of these. How would the reaction do another one? We'd have to do this again, right? Right? And to do this, we need what? Light or heat. Well, something's known about this reaction. You only have to shine the light a little bit at the beginning, then you can turn it off, and the reaction will keep going. How? Because if you turn this off, doesn't it stop this from happening? Well, it should. And if it stops this from happening, there's no more bromine radicals, so how are you going to do anything? Well, that's because the next step is not this taking a bromine radical from this, just these teaming up. Yes, that would give you product, but then you would need more of these and you need more light. Instead, this teams up here. One of these electrons come here, this electron comes here, and you're making a carbon-bromine bond. One electron bromine, one electron carbon. The other electron goes here, and this arrow movement gives what? That gives that, but importantly, plus what? Bromine radical. This is formed without light or heat or anything. Basic, okay? The bromine radical, if we show a mechanism like this, it's formed without heat or light. We don't need the light anymore. We can turn the light off now. We made product, but then this bromine radical can do what? It comes back over here and it serves as one of these, and now it can go react again. Now you come in with your second molecule, you do this. Your second Br2, you do this, but guess what you produce? Bromine radical. Now you can come over here and react with your third molecule and your third Br2, make your third product, but what do you produce? Radical. Then what can it do? Now you can come over here and react with your product, fourth star material. You do this a gazillion times. And we no longer need light, do we? We only need the light over here. This over here is called initiation. Kind of getting the reaction going. At this point, it sort of continues on and on. It's self-sustained. Anybody know what this is called in terms of radicals? Propagation. And you could have a termination step. A termination step would terminate this and then require you to have light, need light again. What would be a possible termination step that would ruin this cycle? Just reacting with something else. Maybe it reacts with another bromine radical. And these team up, what would that give? I guess Br2, but that would be a termination step, right? Because if that happens, we remove bromine radicals and now we need light again. So this is radical chemistry. This is also driven thermodynamically. Making the carbon-bromine bond is favored thermodynamically. You could do calculations here. Basically because the bond you're breaking here, Br is pretty weak, but the carbon-bromine bond is pretty strong. So it's favored thermodynamically. The radicals can be generated by light or heat. You can also generate radicals using peroxide. A peroxide is an oxygen-oxygen bond. And the simplest would be, these would be H's here. And that molecule is called what? With hydrogens on the peroxide? Yes, that's right. Hydrogen peroxide. And hydrogen peroxide is found where? Yes, in your medicine kit. Okay, everybody good? Who does not have hydrogen peroxide in their medicine kit? You don't?
No.
Pick some up, Walmart.
Okay.
All right, 98 cents, right when you walk in the door. You usually got a big old shovel. Right? And when you have a wound or something to cut, put some on. Just don't let it get on your blue shirt because it'll make it fade. These peroxides are also bleaching agents. Okay? Hydrogen peroxide. How do these help? Well, it could be that these make radicals more easily, and these make kind of hydroxyl radicals with heat or something. And then a hydroxyl radical can produce bromine radicals. I'm not going to go into that. There could be questions there, but basically you could show this radical teaming up with here and making an OBr bond and making a bromine radical. In the end, we don't need to get into those fine details here. Peroxides are often added here to form other radicals. Peroxide is added here to help form Br radicals. Okay, you can look up the details if you want. So, or light, or heat, or peroxide. Why regioselective? Well, what type of radical did we make here in this reaction? Tertiary. And what's the best type of radical? Carbon radical. Radicals are just like carbocations. They're electron poor. This carbon does not have an octet. Okay? No octet. What's the charge of this carbon? Well, unless I forgot to show a charge, it should be neutral. It's neutral, right? It owns 4 electrons, both don't, okay? All right, radicals are typically neutral. It doesn't have to be. In mass spec, we see radicals that are cations. Right? Okay. These are neutral radicals here. But since it has no octet, it's electron poor. And how do you stabilize something that's electron poor? You want it to have rich friends. And so we have tertiary with 3 rich friends stabilizing the radical. Radicals are stabilized just like carbocations. Tertiary radicals better than secondary, secondary is better than primary. Okay? Just like carbocations. So the same thing, where's the best place to make a carbocation? Tertiary. Where's the best place to make a radical? Tertiary. And indeed, this reaction will be selected for tertiary radical, and that's why you get the bromide on the tertiary, the bromine on the tertiary carbon. Now, really, but only with bromine. If you try to do this reaction with chlorine, it won't be as selective. All right? Because with chlorine, the reaction is much more exothermic, and it's going to make radicals anywhere. All right? It's like a bull in a china shop. Okay, it's going to come. It's just going to go everywhere. Too much energy. Or it's like water running downhill. Water running downhill, and you got, or down the road, and you come to a fork. You've got a road going up here. Which way is the water going to go? Down. Makes sense, right? That's selective. But what if a hurricane comes? Is it going to go down, only down, or will some go this way? A hurricane comes and the water's going both ways because there's just so much. Okay? That's analogous to if you do chlorination. It's just so exothermic that you lose selectivity. It turns out that bromination is just the right thermodynamics to give you selectivity. All right? Mother Nature has given us radical bromination as a reaction that is useful in the lab to make products. It doesn't mean you can't do chlorination, but it's more difficult and more specialized, etc. Bromination is more common. Now, iodine, on the other hand, you try to do this with I2. With I2, the reaction is endothermic, if you do calculations, because the CI bond is not as strong. And actually, with iodine compounds, they tend to go the other way. You can have an iodo compound, and it will actually eliminate iodine. The reverse of this, and that's shown on the flip side, on the next page over here at the bottom. If you take an iodo alkane, it'll actually go the other way. Now, I'm only showing the fate of the iodine, going back to elemental iodine. Now, I'm not showing the fate of the other here. I'm actually asking a question here. That's like me up here saying if this goes backwards, it will produce bromine, right? Okay, this is going backwards. That's the way. That's a common reaction of iodo alkanes. They actually decompose and eliminate the halogen, I2. Alkyl bromides don't do that as easily because this way is favored, and so it stays here. Okay, there's your mechanism. Predict product here, first reaction. You show product. Yeah? Plus what? Plus HBr, yeah? Selected for the tertiary radical. And in the tertiary carbon radical quenches or captures the bromine radical to make the, well, actually it does not, it reacts with bromine to make a product plus another Br radical, right? Yeah? Methyl cyclohexane, a little bromine, a little light. We've actually sometimes do this reaction in lab. We actually pull out a little light bulb, a little lamp with a little metal thing on it, shade, put it on a clamp, and have your flask here, and shine the light on it. Not very often you leave the light on the entire time, but it is known that you can turn the light off and it will continue. Okay, how about the one below? This is a peroxide, O2. Okay, it's OO. This is a carbonyl phenyl, and so it is a carbonyl phenyl. It's on both sides, carbonyl phenyl. So it can be abbreviated and condensed down to this. The carbonyl phenyl, anybody know the name of this group together? Benzene bonded to a carbonyl. It's called a benzoyl. A benzoyl group. This is a peroxide, right? OO is peroxide. What do you want? What's the name of this peroxide? Benzoyl peroxide, where do you find it at? Also in your medicine cabinet or at Walmart. Okay. And the lotion, skin creams aisle. What is benzoyl peroxide used for? It's used in acne medications. 5% benzoyl peroxide. Okay? But peroxides will kill, it acts as an antimicrobial, just like hydrogen peroxide. These things will form radicals, and those microbes don't like radicals. It reacts to the microbes and kills them. Benzoyl peroxide, yes, it can be used here. Thing about it is it's dry. This is a dry peroxide. Where hydrogen peroxide is always a solution. Pure hydrogen peroxide is explosive. It's always going to be like 30%. Well, in the lab, 30%. At Walmart, it's 4% or something, or 3.5%. Very dilute. Okay. In lab, typically, we have 30% hydrogen peroxide. You would not want to put that on your skin. It will bleach you and burn you. And 100% hydrogen peroxide, you definitely don't want that around, because it probably will explode. Okay. Okay. So what do we have here? We got now you guys don't know aromatic chemistry yet, so we don't have to worry about that. In organic 1, we don't react with benzene with. Organic 2, you'll learn that there may be some chemistry here, but this tells you with the peroxide there, it tells you it's radical. And since it's radical, where's the best place to make radical at? Same as cations. Where's the best place to make carbocation? There's no tertiary carbon here.
Secondary next to
Primary, secondary, tertiary, that terminology is really only used for an sp3 tetrabutyl carbon. So while that is a tertiary carbon in terms of bonded to 3, right? That carbon's bonded to 3 others. I would never really call that a tertiary carbon. Only sp3 carbons do we use that terminology. All right. Secondary right here. That's where you would make carbocation, because it would be benzylic. It's also where you would make radical. And the bromine radical will strip an H from there. Same mechanism as above. The peroxide helps us make bromine radicals. It strips an H from there. And then that reacts with bromine to get a bromine and reform bromine radical. Same mechanism as above. But the product here is what? Just here, yeah? Plus HBr. A couple things here. We have a carbon. Will it be R or S? The carbon is now chiral. R or S? R or S?
S.
Why would it be S?
Because the BR is a high-priority group and then going counterclockwise.
Yeah, but I did not draw it in. I drew it very generically. Is the bromine going forward or back? The way I drew it, I'm not showing you any stereochemistry. So you cannot determine RS from my structure. But will it be R or S? It will be both. It will be racemic. If it's only S, we get Nobel Prize. Okay? Is anything over here optically active? Is this optically active? Is it chiral? No. Is anything here optically active? No. If nothing over here is optically active, your product cannot be. And it's not. Why is it not?
Because it attacked a...
Because it's racemic. Racemic mixture is not optically active. 50-50, they cancel each other out. Okay? So if you remember that rule, it's going to be racemic. Okay? Why? Well, basically, what's the hybridization of a radical? The geometry of a radical. Hybridization of this carbon radical.
It's the last piece.
How many regions around it? There's one H there. This actually is kind of counterintuitive. No, it's not, if you consider one thing. What's hybridization of that there? What do you expect for it? Hybridization? Michael? Two? Why?
The radical, the electron, the same electron would be in the pure world because it's making a signal lines to.
Yes. Yes, it's just like a lone pair. If there was a lone pair here, it'd be in a p orbital because there's p orbital next door. Well, guess what? If it's only one electron, same thing. Electron's going to want to be in a p orbital. Okay? And it's a single electron in a p orbital. Why? Because it's resonance stabilized. And all that. Okay? Yes, it is sp2 trigonal planar. Since it's planar, okay, planar, the other bromine either comes from the top or the bottom. And that's how you get both R and S. Okay? Well, let's look at, can you do resonance of radicals? I'm going to go back to here. Yes, you can do resonance of radicals. Here we go. You move one electron here and team it up with that one. We're going to make pi bond here. The other pi electron we move here. What does that give? Pi bond here, because two electrons teamed up to make additional bond, it will be a pi bond. One electron moved out here. Nothing here or here. Nothing moved there. There you go. That's an alternative Lewis structure for this. We call that a resonance structure. And you can keep going. You can put the radical here and here as well. Move electron pi bond here. Okay? You can do resonance of radicals. Now there's no charge here, so we're not delocalizing charge, but we are sort of spreading out this single electron. It's not sitting on one atom. And so that's another reason you would put it here. Not only is it secondary, because look, both of these carbons are secondary. Why would you rather make radical here than here? Because radical here will be resonance stabilized. And yes, that one electron's in a p orbital, just like a lone pair would be. Okay? So that's why you would get selectivity there. How about the next reaction? NBS. NBS is N-bromosuccinimide. It's a source of bromine radicals. It's an alternative to Br2. With light or peroxides or anything, this will do this. And by the way, we didn't define this. So make a nitrogen radical plus Br radical, but it's a source of Br radicals here, just like Br-Br. An important term here is we're cleaving this bond, but this is homolytic. Okay? We could have shown this when we did the Br-Br over there originally. Okay. What is homolytic bond cleavage? Homolytic bond cleavage, when the bond cleaves Each atom gets 1 electron. Okay? On the other hand, if you took HBr and the bond cleaves by ionization, what happened? Yeah? And we get what? H plus? Br what? It took both of the electrons, right? Took both of them. And that's now a minus. And since it took both of them, it left this over here as a plus. And we call this ionization. Do we call this ionization? No, we didn't make any ions. The bond broke, but over there it was a homolytic bond cleavage. The atoms got the same result, 1. This is called what type of bond cleavage? Heterolytic bond cleavage. Different outcome. One atom got 2 electrons, the other atom was left with none. Okay? So homolytic bond cleavage gives you your bromine radicals, either from Br2 or NBS. Good thing about NBS is, compared to bromine, bromine is a toxic, volatile liquid. All right? If you drop a bottle of bromine, you're going to have this nasty liquid everywhere. You're going to have to evacuate the lab. All right? You got to have good ventilation, et cetera, et cetera. NBS is a nice white solid. Color really doesn't mean anything, but it's a solid. You can weigh it out on the balance. You drop it, you can sweep it up. Which would you rather use? I'd rather use NBS. It's much more user-friendly. Okay? Down here we have 2 possible products due to resonance. Please show them both. Okay? And also answer this question. Why can't you use Br2 in the last example? Why is NBS better here? We need to talk about that. Particularly, why can't you use Br2? What else could happen there? Okay, we'll finish this handout up pretty quickly next time. Please look ahead. Got the entire handout. Entire handout. See some of you this afternoon in lab for checkout, then we'll come downstairs.